Okay. Trinity, could you do me a favor and hand one of these to everybody in class? Okay, so today's a half day, so that's cool. So we're going to have a shorter class than usual. Also, smile to the camera. I'm recording myself for my student teaching again. Okay, so everybody go ahead and grab your books and open them up to page S47. Trinity is passing out a sheet of graph paper to everyone. Let's go ahead and get started. Now, yesterday and Friday, we learned some things about random distributions. We learned about the difference between discrete and continuous variables. Yesterday, we learned some facts about random distributions. We learned that the sum of all the elements in a random distribution will always add up to what? 1, yeah. Okay, so on S47, Module 5, you see there a table. A table tracking number of credit cards and the relative frequency that a household that a person has that number of credit cards. Fair enough? Is the table clear, easy to understand? So about 26% of people have 0 credit cards, about 17% have 1, and so on. Your opening exercise is to do problem 1, which is to write a histogram, or to draw a histogram for this table. What's a histogram? Yeah, a histogram is it's a bar graph, essentially. Okay, so think you can do that? Go ahead and draw a histogram for this graph. How many bars will this graph have? 11, yeah. It goes 0 through 10, so that's 11 bars. Okay, now our class is short, so don't dawdle. I'm going to go ahead and take attendance. You should be able to finish this in 3 to 5 minutes. Let's say 4 minutes.
I always do it. It's like there's always
On the graph paper. Draw the histogram on the graph paper. Yeah, it's that we're doing problem 1 in the book, but you're doing it on the graph paper because it's easier to draw on the graph paper. I'm gonna have to draw it on the board, poor sap that I am. Okay, then attendance, Trinity.
Here.
Sonny.
Here.
Mortice. Here. Kylie.
Here.
Chelsea. Liliana.
Here.
Edwina.
Here.
Zebedee.
Here.
Tishana.
Here.
Megan.
Here.
Audrey.
Here.
And Lena.
Here.
I can make my life easy. You are on the right page. That's 47. That's what you're trying to do. So. It doesn't have to be perfect. 47. No wonder you were confused. One minute. Okay, so that was 4 minutes. So mine is going to be considerably less pretty than yours because I don't have a graph board. So, how many columns are there again? 11? Okay, so we have the 0, 2, 3, 4, 8, 9, 1, 2, 3, 4, 9, 10, and 11. Or, so, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so help me out with the vertical scale here. So, what do you think? How do you think we should label this scale here on the left? Do you think it by fives? Or so that's going to be, you mean like 0.05? Yeah, 0.05. So yeah, that makes sense. So let's go up to 0.3 because our highest number is 0.27. So that's a little bit higher. Okay, so half of that, that's 0.15. Half of that there, that's yeah, that point there, that's point. Whoa. I'm apparently bad at math at the moment. Okay, so. No, there should be 6 sticks. So that's 0.5, 0.1, 0.15, 0.2, 0.25, 0.3. Okay, fair enough. Okay, so how high is the 0 column going to be? That's 0.27. So it's about halfway between. Okay, next one. Help me out. Next.
0.12.
It's like here.
0.10.
0.10. That was nice and easy. Next.
0.09.
Say what?
0.09.
0.09. Okay, so only just a tiny little bit shorter. Then
0.06.
0.06, so a bit of a bigger drop there. Then
0.05.
0.05. That's 0.05 again, right?
Yeah. 0.04 is next.
Then 0.04.
0.03.
And then 2.03s. Okay. So go ahead and work. You can work alone or with a partner. And go ahead and answer the different questions in problem 2 on the next page. Not all of us have made our graph. Problem A is asking you to describe the graph. You can just describe it using regular, boring old English. How would you describe the shape of this graph? Problem B is asking a question about what's more likely, having 0 credit cards or 7. 7 or more. Find the area of, then it wants you to find the area of some of these bars. How do you find the area of a rectangle? It's length times width, yeah. And D wants to know what is the total area of all of these bars. You should be able to answer all 4 questions in 4 minutes. You can answer in the book or on the graph paper. Let's go. Okay, so we need to find the area of each of these bars. Okay, so area is length times width, right? How wide is this? How far is it from here to here? 1, yeah. 0 to 1. So the length width, it looks like 1 to me. And how tall is this one? So, full 20 times width, what do we get? Area. About 50 seconds. Okay then. So I'm not going to, everybody will have their own answers for 2A. But how would you, how would you describe it? Describe this shape to me. Let's just kind of just try to describe the important features of this shape. So it's decreasing over time. Does it have any bumps anywhere, or is it a smooth decrease? It's a pretty smooth decrease, yeah. When I look at this, I see maybe an exponential decay curve. You know, something that starts steep, then gets shallower and shallower as we go. Okay, so there's no bumps anywhere. It goes steadily. And where's its maximum value?
Zero.
At 0, yeah. So everybody will use your own words to describe this. So I'm not going to tell you what to write. Just describe what you see, and I'm happy. Now, problem B wants to know, is a randomly selected adult more likely to have 0 credit cards or 7 or more credit cards? So how tall is the 0 column?
0.26.
0.26. So, and what are we comparing it to?
7.
7 or more? So is that this column right here? It's not. It is this column, but what else is it?
8, 9, 10.
8, 9, and 10, yeah. So how tall is the 7?
0.26.
The 7 is 0.25, or is 0.05. It's the 0 that's 0.26. So we have here a 0.05. And this, how tall is this one? And these two? Those are 0.3s each. So that's, add them up, that's 0.06, 0.1, 0.15. So what's bigger, 0.26 or 0.15? 0.26. So the 0 is more likely. Or rather, you are more likely to choose to select a person with 0 credit cards than a person with 7 or more credit cards. Now C is interesting. This is something you may not have done before. We have to find the area of this bar. So how wide is it? How far is it from here to here? The distance there is 1, isn't it? So I saw some people write their histograms in different ways. I saw some people do it, so that the 0 is here, like the left edge. Others have the 0 in the middle. But either way, that distance is still 1. So the area of a rectangle is, or its length times height. So from here to here, what's this distance? And from here to here? And 1 times 0.26 is 0.26. 0.26 what? 0.26 miles? Do we have a unit here? Are we given a unit? No. So when you're not given a unit, you should just say units. Yeah? So that's 0.26 square units. And D, what is the area of all the bars in the histogram? So we need to find out not just the area of one bar, but the area of all the bars. Oh man, that might take a little while. Unless anybody knows a shortcut, something we can already know. Let's see. We have here, each of these is probability, right? So what's the sum of all of these probabilities going to be? 1. The sum of probabilities, the sum of all probabilities in a given experiment is always 1. And when I multiply by the width, is that going to change any numbers? The numbers? No. The area of each of these is going to be equal to its height. And if I add up all these heights, what am I going to get? 1. Because the heights are the probabilities, the area equals the height. So the area of all of these is just 1. Fair enough? So, because the area of each rectangle equals its probability, the total area is 1. This total area equaling one thing. It's really important in a lot of statistical applications. It's used a lot in science for things called Gaussian distributions. Just something that might show up in physics for those of you taking physics in college. Though this is itself not a Gaussian distribution. And this idea of finding the area underneath the graph is very important in calculus. Basically, a third of calculus is going to be finding areas under graphs. So those of you taking calculus either next semester or next year, you'll be seeing these a lot. All right? Okay. So for problem 3 is, you can almost think of it as almost a true or false situation. It's saying, hey, we performed a survey. We randomly asked 500 people how many credit cards he or she has. So this is a different survey, but with the same. This is a different survey, but with a similar population of adults. And it wants to know, and you're asking these 500 people how many credit cards they have, and A, B, and C is asking you if you would be surprised if certain results come up. So, part A. Let's do part A together, then I'll have you B, C, and D. I guess there's a D up there. Off the other side. Ooh, I missed that first hour. So let's look at part A together. If I ask a group of 500 people how many credit cards they have, and nobody in that group says 0, if everybody has at least 1 credit card, would that be surprising or would that be expected? See, I'm hearing some surprising and I'm hearing some expected. Okay, I'm going to use a jar of doodle here. Put somebody on the spot. Who's this? Lionel. Do you think that would be surprising or would that be expected if when we survey 500 people, none of them have credit card, or all of them have at least 1 credit card?
Surprising.
Why do you say that? Well, let's look at this here. What percentage of this group doesn't have any credit cards?
10.
10%? Which of these columns is the one that represents no credit cards? It's the 0 column, yeah? And so that's 0.26? 0.26, what percent is 0.26? That's 26%, yeah? So if I ask 500 people, if I do another survey and ask 500 people this question, about how many of them would you expect to say, I don't have any credit cards? About what percent of them would you expect to say that? About 26%. It's a randomly selected group, so you're not going to get it exactly the same, but you should see something kind of similar, right? And is 0 anywhere close to 26%? No. So would that be surprising or would that be expected? That would be very surprising. So really quick, so we would expect about 26% of that 500 to have no credit cards, right? So what is 26% of 500? Okay, let's round it off a little bit. 26 is pretty close to 25. What's about 25% of 500? Hey guys, what's 25% of 100? So 25% of 100 is 25. So let's just multiply that by 5. What's 25 times 5? So we'd expect maybe something like 125, maybe a little more. 131, maybe. Make sense? So I would say that would be surprising. I would expect about 125 people to have no credit cards. Do you think you have a handle on this, or do you guys think we should do another example together? So you raise your hands if you think we should do another example together. Raise your hands if you think you got this. Okay. Okay. Looks like there's some confusion out there. Let's do part B together. But then I really am having you do C and D all on your own. So part B is making the statement, 65 people have 2 credit cards. Out of how many people? How big is the total group? 500. So about what percent of the group would we expect to have 2 credit cards? You can look at your table if you want to get the exact numbers. About how much?
12%.
About 12%? Okay, so what's 12% of 500? Calculators available for use if you want. So about 12% of 500 is what? 60. And how'd you get that number? Yeah, multiply 500 by 0.12. So this survey got 65. The 12% of 500 is 60. So do you find that result surprising or expected? That seems pretty expected to me. That's, 65 is a little high, but only by a little bit. Yeah, we'd expect things to be going up and down a bit. There should be some variance there. So I would say that would be expected. 12% of 500 is 60, which is pretty close. To 65. They aren't exact matches, but they don't have to be. We're not expecting them to be exact. We just want them to be in about the right area. Make sense? Okay, think you have a better handle on this? I hope so, because you're doing C and D on your own. C and D is expecting C and D is telling you that their survey had 300 people with at least 3 credit cards. That's 3 or more credit cards. You need to find out what the expected number would be, and then compare our expected number to the one they got. Feel free to work with a partner. Part D is saying, hey, we had 150 people who had more than 7 credit cards. There's more than 7? Yeah, more than 7, so that's 8, 9, or 10. Is that expected, or is that surprising? I think we should be able to solve this problem in about, I'm feeling generous, let's say 3 minutes. Still rolling. Thank you, Miss. Is it saying at least 3? At least 3 or more. Okay. So, problem C is saying that we're expecting, problem 3 is asking us if it's expected or surprising that 300 people had at least 3 credit cards. And when I say at least 3, who's included in that group? That's 3, 4, 5, 6, 7, 8, 9, 10. And apparently nobody has anything more than 10. Okay. So, well, let's do it. So, how are we going to find the probability of someone having 3 or more credit cards? What will we do with all these columns? Huh? What do we do with them? We'll add them. So, 0.10 plus 0.9. See, using our calculators. That's 0.19 plus 0.6 plus 0.5 plus 0.5 plus 0.4. Oh, that's 0.05, not 0.5. Okay. Whoops. Okay, plus 0.4, or plus 2 plus 0.2. I messed it up. Plus 0.06 plus 0.04 plus 0.06. So when I added all these up, when I added the 3 or more up, I got a total of what? What did you guys get? When we add up all of these from 3 down to the 10. I got 0.45. Okay, so what's 500 times 0.45? That's 225? So what do you think? We're expecting 225, we got 300. Do you think that's surprising or is that about expected? It's kind of almost borderline. I look at it and I kind of see that as kind of surprising. 75 is a pretty big chunk of people, but maybe you disagree. This is data analysis, son. But There's room for interpretation. Personally, I would find that surprising. But you might disagree. It kind of, that's about 225 and 300. That's a 25% difference. So, whether you see that as being close or far, that's kind of up to you. We don't have it well defined here. Okay, D is making the statement 150 people had more than 7 credit cards. Let's see. So that's just for the more than 7 group. So that's 0.06 plus 0.04. That's what? 0.1? So it's 10% to 500? 50. So we are expecting 50. We got 150. Do you find that surprising or expected? That is definitely surprising. That is 300% difference. So C is kind of, that's kind of up to your own interpretation. But D, that's very unexpected. Okay. I'm just trying to do that one. Okay then. I'm going to have to cut off a big chunk of this lesson because today is a half day. Okay, so let's go ahead and turn the page. And let's look at, or turn the page up to S52. So that's turn twice. Yeah. So let's take a look at problem set 1. Don't fling ramen around my classroom. I'm assuming that. Okay, so for S52 we have 4 histograms. Now what it wants to know is which of the following could be a graph of a probability distribution. So in other words, which of these could be a graph of probabilities? Let's see. Now all of them seem to have variable on the x, probability on the y. There's something kind of odd about part A. Anyone see something that doesn't make a lot of sense in part A? Okay, so there's 2 really high ones. How tall are those high ones? They're going up to 0.6, and so together, what's the area of just those 2 right there? That's an area just between those 2 rectangles of 1.2. And what is the total area of a probability distribution going to be? 1. So could that one possibly be a probability distribution? No. Your job in B, C, and D is to figure out if each of those could be a probability distribution. Make sense? Okay, this is pretty easy. It should take you no more than 2 minutes. And setting timer for 2 minutes. That's fine. Okay. Okay. So for part B, that first, what's the area of that first column? That's 0.5, the area of the next one? Area of the next one? What's that spell? 1. It adds up to 1. So could that one be a probability distribution? Yeah, it adds up to 1, which is what we need. What's up? Yes, you may. Now then, part C. Well, let's see. It goes 0.3, 0.1, 0.2. That's 3, 1, and 2. That adds up to 0.6 in that first part. The next one is 0.4. Oh, we're already at 1. Then 0.5, 0.6. That adds up to 1.6. Would that be a probability distribution? So C's a no. And D. D goes 0.1, 0.1, 0.2. So that's 0.4 so far. Then 0.1, 0.2, 0.2, 0.1, that's 0.6. 4 and 6 makes 10, so it adds up to 1. Sweet. So part D, is that a yes or a no? That's a yes. Okay. Okay. So we have about 7 minutes left. I think I will go ahead and pass around the answer. Sound good? Okay. So today's lesson is kind of had to rush through it a little bit. Mr. Von Rensselaer? I remember Jeffrey Von Rensselaer. My first job here was when I was a substitute teacher. I was having my first day. Oh, so you're only in Von Rensselaer today? And you transferred into Von Rensselaer. Well, I probably was your substitute teacher for 2 days then. I don't know. Do you remember a flustered and kind of dorky substitute teacher? Oh, now they remember.
No, you said something about your dad.
Okay. So this exit ticket is pretty much exactly the same as that rising versus expected thing we were doing a few minutes ago. So here we have a table. Did I miss anybody? No? So we have a table showing number of songs and probability. So if you give the survey again to a random sample of 200 students, A, B, and C wants to know if those results would be expected or unexpected. Sound good? Now, whether something is reasonable or unreasonable, that's kind of up to you. What I really want to see is I want to see you supporting these thoughts. Why do you think it's reasonable? Why do you think it's unreasonable? When you're done, as always, go ahead and call me over. I'll check. Everything going okay, Drew? That awkward moment when you realize that this is what you're watching actually. Gonna have to give you guys another problem. Yes. So I done messed up. I'm sorry. I don't. If once you're done with this, I'd like you to try problem 3 on page S53 in module 5. You to work with the bell after all. See if I did this with my watch. It's actually the right one to do. Still. So for number 53, I have a table that shows a random distribution for rolling a die, but an X is in there. Wants to know what number you're plugging the X that would make that actually make sense. Then it wants to answer a few questions. It's pretty sure. Okay, Morgan? So when will it die? What should the probability of each base be? So, you know, how many bases are there? And how many of those? So that the probability of that would be 1/6. See, probability of each base is 1/6. So what can I plug in to this? What can I plug into the X to make all of these actually make sense? Okay, if you haven't turned in your exit ticket, turn it in to me, show me your work, and you show me your problem number 3 is, put your step away. I already saw yours. You did not get to it, no.
Diana Rose Begay to the front office. Diana Rose Begay to the front office. Teachers, please take your attendance the first 5 minutes. When you are taking attendance, make sure you make one click. If you make double click, it will go and mark the student absent or tardy.
So the probability of any one.
So make sure by the end of the day,
so we need to plug in a number that would make each one become 1.
Which students were absent and tardy, double check your attendance, please. Thank you.
What are we doing today?
We are doing that.
Football and cross country
we are moving on to the next lesson.
Are in. Pick it up in Mr. Holliday's office.
Okay, that was my observation.